This is now the last video of applied microeconometrics, and today we're going to look at a new topic, and of course then also the last topic, and that is sample selection models. And even though I would like to ultimately look at so-called non-separable sample selection models, which is much more in line with what we have done so far because of the fact that that is related to quantile regression models, and is by the way also related to my own research. What I'm going to do is that I'm going to start with standard sample selection models. I'm not sure whether you have already heard about this before. If you have already seen this before, then this might be a little bit of repeating, but it never hurts to see two things or one thing twice. So the model is as follows. We have, usually we have two different equations, but here I have written it down in three different equations. The first equation is usually called the outcome equation, and it has a yi at the left hand side, and on the right hand side we have beta 0 plus beta 1 xi plus ui. And what we're going to assume is that yi is only going to be observed in the case that I is equal to 1. So even though this relationship might be interesting for everybody that we have in our population, we can only observe it, we can only observe yi at the moment that another random variable I is equal to 1. Xi is going to be always observed, as well as I is also going to be always observed, and the same is actually true for Zi that we have here in the second equation. Talking about that second equation, it has hi star at the left hand side, which is actually an unobserved variable. And at the right hand side we have gamma 0 plus gamma 1 xi plus gamma 2 zi plus vi. And then the last equation that we're going to have over here, this is usually called the selection equation. Well, it says that when hi star is larger than 0, well then at that moment in time I is equal to 1. So that is the situation in which we're going to have that we observe this relationship over here. If hi star is going to be smaller or equal to 0, well then at that moment in time we're going to see that I is equal to 0. Well, we are going to make a couple of different assumptions with respect to this model that we have over here. First of all, xi, zi, ui, and vi are going to be iig just for convenience. And in addition to that, we're also going to assume that u and v, or u1 and v1, they are uncorrelated with x1 and z1. Well, the question of course always arises at the moment that we're going to look at the theoretical model is whether this model is only interesting in theory or whether this model itself also has applications. Well, this is applied microeconometrics, so therefore you might expect that it also has its own applications. And that's actually true because of the fact that even the model that we have looked at so far, or in a sense the applications that we have looked at so far, actually fit into this model that we've over here. Remember that we already looked many times before at the relationship between the log wages of somebody and, say, the characteristics of that particular individual, the so-called human capital characteristics. Well, including, of course, the education level of an individual, ethnic background, gender, region, etc. But we should now realize that even in the case that we are going to assume that the x's are going to be completely exogenous, which is of course not the correct assumption at the moment that we have education here at the right hand side, but let's assume that even education here is completely exogenous, or at least we don't want to take that into account. Then still at that moment in time we should realize that we have a problem over here. And that is that wages can only be observed for those individuals that work. Usually, how do we get wage data? Well, we should realize that wage data are usually either from surveys in which people asked what their wages were in a particular period of time, or we get them from register-based data sets, which means that we essentially get them from the tax office. Well, then you should realize that, well, of course, wages are well known at the moment that somebody has been working in the previous period. But you should take into account that the wage of somebody that has not been working, well, that is not going to be observed. Even though we could, of course, think about the fact that people, even at the moment that they do not work, they have a potential wage. They have a potential wage that they would have had in the case that they would have decided to work. Take into account that, of course, there are people who are completely unemployed, but there are also people that simply decide not to work. For example, because of the fact that they are going to education, they are going to school, but it could also be because of the fact that they decide to take, for example, care of children. These individuals may have had a wage at the moment that they would have decided to work, but we do not observe them simply because of the fact that we are, well, they do not work. And therefore, we are not able as econometricians to observe those wages. Well, take into account that since U and X, they are uncorrelated to each other, if we would have had this relationship for everybody in our population, then at that moment in time we could just have done an ordinary squares regression of y on x, and then ordinary squares, given this assumption that we over here, would be consistent and unbiased. So then we would get unbiased and consistent estimators of beta 0 and beta 1. However, that is not possible in this case because of the fact that we do not always observe this y I that over here. So then the question arises, what could we do instead? Well, the simple answer to that question is we could, of course, just simply run a regression now of y on x on those observations that we actually observe for which I is equal to 1. This is usually called the so-called selected sample. We can look at the subsample for which we do observe yi and then simply run an ordinary squares regression. But we should take into account that that actually does not work. Even though we have that we can do an ordinary squares regression over the total population, but we, of course, that is not feasible because of the fact that then yi is not always going to be observed. But we cannot do, at least we are not going to get consistent and unbiased estimators at the moment that we're going to do an ordinary squares regression only on the so-called selected sample. In order to explain that, the best thing that we can do is that we can look at the mean of y1 conditional on x1. That's typically what we do at the moment that we are going to look at ordinary squares. Then we look at the mean of y1 conditional on x1 equal to x, because of the fact that that should be equal to, well, beta 0 plus beta 1x. That's what we know from, say, very first year or maybe second year econometrics. But in this case, we cannot, of course, look at the mean of y1 conditional on x1 equal to x. And the reason behind that is because of the fact that we do not observe always this y1 over here. So therefore, apart from the fact that we're going to condition here on x1 equal to x, we're also going to condition on the fact that I must be equal to 1. Well, apart from that, I'm also going to, well, condition here on z1 equal to z. So therefore, we get this mean that we have over here. And the question arises, is that equal to beta 0 plus beta 1 times x? Well, this we can quite easily calculate, of course. We can calculate this to be equal to the mean of, well, what we can do is that we can substitute in here this model. y1 is, of course, equal to beta 0 plus beta 1 x1 plus u1. And then the next step that I can take is that I can also realize that I do know what it means that I is equal to 1. I equal to 1 means, of course, that hi star should be larger than 0. It means, of course, that this whole thing that we have over here should be larger than 0. So therefore, we can also write it now like this. And then we can use a trick that I already have used many times before. Well, we see that this x1 is exactly the same as that x1 that we have over there. Here we condition on x. So therefore, we can also write this as little x. And the same we can do with respect to this x1 that we have over here. Well, we can even do the same with respect to this z1 over here, because of the fact that we also see that here this z1 is exactly equal to that z1 that we have over there. That one is equal to little z, so also this thing that we have over here could be written as little z. So therefore now we get all these things that we have over here. Now we see that this is actually a mean of a sum. We know that that's always sum of means, so we can now write this as the mean of beta 0 first of all. But beta 0 is completely deterministic, so therefore we can simply write it as beta 0 itself. Then we get the mean of beta 1 times x, but also beta 1 times x is in this case completely deterministic. So therefore we can also write this now as beta 1x itself, plus of course the mean of u1 condition on all these things that we have over here. So we can now write it like this. Well, then the next step that we can do is that we can realize that here, at the moment that we look here at the left hand side, the only thing that is really, say, still stochastic is phi1. So it would be better to take all these things now to the right hand side to write it in this format that we have over here. And then the next step that we can take is that we do of course know that u1 and v1, they're uncorrelated to x and z. So therefore we do not have to condition here on x1 and z1. So therefore I can even write it in this format that we have over here. Now we have a much nicer equation, but we immediately see that there is a problem, because of the fact that what we wanted to have is beta 0 plus beta 1 times x, but instead we have beta 0 plus beta 1 times x plus an additional term. Well, we do not always know how this actually looks like, and we also do not know whether it is equal to 0 or not. Generally this term is not equal to 0, and it actually depends on x and z that we have over here. But the question of course arises, when could this be equal to 0? Well, the first situation is that, well, if u1 and v1 are going to be uncorrelated to each other, well then of course this term that we have over here is equal to 0, because of the fact that then at that moment in time we should realize that we do not have to condition then on the outcomes of v1, also not on whether v1 is larger than this thing that we have over here. So then we can drop this whole part over here, then we still have the mean of u1, but that is equal to 0. So therefore if u1 and v1 are going to be uncorrelated to each other, well then we should realize that then actually ordinary squares still works. But the question of course arises, is that a very, well, reasonable assumption to make in our context? If we, for example, are going to look at the log wages, running regression of log wages on the characteristics of individuals, well then you should realize that that actually might not be a very good assumption to assume that the u and the v, they're uncorrelated to each other. And the reason behind that is because of the fact that you should realize that in labor economics, I'm not that sure whether you have had a lot of labor economics before, but in labor economics we usually assume that people, they are only going to work at the moment that their wage is above a certain threshold, which is usually called the reservation wage. Maybe you have heard about this before. This implies that we assume that people don't really like to work. It's not that they just work because of the fact that they think it's fun. People usually work because of the fact that they get a wage for that, that they get money for that. That's the reason why people work. And you should realize that well, if you only get, for example, 1 cent per hour, then most people would say like, well, I'm not going to work for just 1 euro cent. Also, at the moment that you're paid only 1 euro, well then a lot of people may actually say like, well, also then it is better not to work at all. But if you're paid 10, 20, 30, or maybe even 50 or 100 or 200 euros, then things are going to change, which of course indicates that usually we can expect that you only work at the moment that your wage is above some threshold, which is usually called the reservation wage. But what does this mean? Well, this means of course that people generally are going to be observed if their wages are relatively high. That is of course related to the observed characteristics. This is probably also the reason why we usually see that individuals with high levels of education are more likely to work than individuals with low levels of education. But this can also be related of course to the unobserved characteristics here in VI. We can expect that individuals that have a relatively high level of VI, so therefore relatively likely to work, well, these usually are also individuals with relatively high wages. But having relatively high wages, well, conditional of course on your observed characteristics, means a relatively high UI that we have over here. And that means that we could, in this particular example, in this particular application, we might expect that U and V could be correlated to each other. And we may even expect that they could be positively correlated to each other. So therefore, assuming that U and V are not correlated whatsoever might not be a very good assumption to make. However, there's also another situation in which ordinary square still works. And that is the situation in which the probability that phi1 is larger than minus gamma 0 minus gamma 1 times x minus gamma 2 times z. This, by the way, is usually called the propensity score. It's the probability that you actually participate, or at least the probability that I is equal to 1, because in the fact that take into account that if phi1 is larger than this thing that we have over here, well then also hi star is going to be positive. And that means, of course, that condition on your x and z, that is the probability that you actually have an I equal to 1, this I that we have over here. And that you actually do observe this yi that we have over there. Well, if this propensity score is exactly equal to 1, well then we should realize that we also can still use ordinary squares. And the reason behind that is that if, say, the probability that phi1 is larger than minus gamma 0, minus gamma 1x, minus gamma 2, z, if that probability is equal to 1, well then you should realize that this part that is over here becomes completely deterministic, because that's the same. Having a situation in which a particular outcome has a probability equal to 1, that's the same as say that something is deterministic. So therefore we don't have to condition on this thing that we have here anymore, and therefore we can simply completely cancel out this term that we have over here. Now the question of course arises, what does this mean? What does it mean that phi1, the probability that phi1 is larger than minus gamma 0, minus gamma 1 times x, minus gamma 2 times z? What does it mean that this probability is equal to 1? Well, that means actually nothing else is that generally you do have a sample selection problem, in a sense that there are always individuals that could have an x and z and a v that are not going to be participating in the labor market, or at least in a very general context, are going to, well, not be observed with respect to their y. There may be, say, individuals with a certain x and z that always are going to have an I equal to 1, because of the fact that if this is going to be true, well then it actually means that whatever vi is, hi star is always going to be positive. And therefore I is always going to be equal to 1, which means that y is always going to be observed. Which means essentially nothing else is that even though there is of course generally a sample selection problem for the people with general x's and z's, there may be a subpopulation of individuals that have x's and z's in such a way that they will always be observed. In our application, going back to our application, we could also ask ourselves the question, could there be individuals that are always going to be observed? Well, that's difficult to say whether people that are always going to be working, but if you ask me, then I would expect that generally still going to be usually men that have relatively high probability to work, and especially young men. So suppose that we're going to look at young men between 25 and 35 that are very high educated and that are living in, say, very good areas in the bigger cities. You could actually say these are the typical yuppies, as we call them usually. Well, these are of course individuals that are very likely to work, and it would all even be maybe a little bit strange if you have a yuppie that actually doesn't work. I have never seen in my whole life a yuppie that actually doesn't work. So you should take into account that well, this might be a subgroup for which indeed this propensity score is exactly equal to 1. Well, then what we could do in that particular context is say like, well, then on that subsample we can run a regression of y on the remaining axis that we still have. Of course, not on the axis conditional on, say, education level being very high and say a man and a person in between 25 and 35 years old and living in a particular very good area in a big city, but maybe we can still take other things into account in order to be able to estimate their beta coefficient. But take into account that this still is, well, difficult to do, especially because of the fact that there will not be that many, say, observations for which this propensity score is exactly equal to 1. Even for yuppies, it might be possible that there are some yuppies that at a particular moment in time decide not to work, and therefore we do not observe their wages. And of course, you should also take into account that these are individuals that are very special, and therefore to do a regression and to try to get the beta coefficients for the total population might be relatively difficult. So therefore, we must admit that generally, of course, these propensity scores are not going to be equal to 1. They're not going to be equal to this 1 that we have over here. And then the question, of course, arises, what can we then do? Can we then say something about this, what we usually call bias term over here? What we want to estimate, of course, with the conditional mean is beta 0 plus beta 1 times x, but in reality we get this additional term. We usually call this the bias term over here. If we would have known this bias term, then it would not have been a big problem, because of the fact that we can always then take that, say, bias term out, and then still actually what we can do is that we can bring that to the left hand side, for example, and then still estimate beta 0 and beta 1. But generally you do not know how this bias term looks like. However, one thing that we know for sure is that this bias term will, in absolute values, become less important at the moment that the propensity score becomes larger. So for example, if U and V, they are positively correlated to each other, that's not necessarily the case. They could also be negatively correlated to each other. But if they're positively correlated to each other, then what I said means that at the moment that the propensity score becomes larger, then this value that we have over here becomes smaller. And that's not that difficult to understand. First of all, remember that what I said was that at the moment that the propensity score becomes in a limit equal to 1, well then this term that we have over here becomes equal to 0. Well, propensity score equal to 1 is the highest potential propensity score that we can actually have. And then we are going to see that we are going to have an outcome equal to 0, also the lowest outcome. But what happens at the moment that the propensity score is not large, but for example very small? What happens, for example, if you're not going to look at the subsample that is going to, well, very likely to work, but suppose that we're going to look at a subsample of individuals that is very unlikely to work. For example, again, at the moment that we're going to look at the individuals that are going to, well, be in the labor market or not, then we can, for example, think of, well, women instead of men. Women still have a lower likelihood to be working in general. And let's now not look at, well, high educated men or high educated women, but now instead look at a situation in which we're going to look at a very low educated woman. In addition to that, we're going to assume that she has young children. And, well, if she's married, then she's married to somebody that doesn't make that much of money. Well, then you should realize that then in those cases, and, well, let's assume for the last part that she actually lives in an area where actually the house prices or the average wage rate of the individuals is also quite low. Well, we should realize that if an individual has these kind of characteristics, then it's generally the case that the likelihood to be working is going to be very, very small. At least it's going to be less than 50%. But that, of course, doesn't mean that there are no, say, low-educated women with children at home and who live in, say, not the very best neighborhoods. That it's always going to be the case that these women actually don't work. There are women, of course, with all these kind of characteristics, and even though their propensity score is low, they still are working. But you should take into account that these are very special persons in this case. They're not representative for the rest of the population because of the fact that they usually then have to have, if there is positive correlation, then they must have a relatively high level of V in order to be working, that's general. And if there's positive correlation, then they must also have, say, a very high level of U. In our case, a very high level of weight. So that means that they're not really representative. And that means, of course, that this bias term that we have over here is going to be very, very large, because we're going to look at the subpopulation of individuals that are not representative for the rest of the population, because of the fact that they are very special and the rest of the population is actually quite large. So that means that the lower the propensity score, also the higher is going to be this bias term that we have over here. But other than that, we do know that this bias term is decreasing in absolute values at the moment that the propensity score becomes larger. Other than that, we don't know that much about this bias term. Unless, of course, we are going to make additional assumptions. Well, that's what we typically do in econometrics. At the moment that we do not know what something is, then we could actually make parametric assumptions. Especially in earlier days. Now it's not that popular anymore. But in earlier days of econometrics, at the moment that you were not able to make calculations anymore, then you're simply going to assume a particular distribution. And in this case, we could assume a distribution for U1 and V1. Let's assume it to be joint normal. So that means that both U1 and V1, they're going to be normally distributed, but they're also going to be correlated to each other, and the correlation coefficient is going to be equal to rho. Well, then at that moment in time, you can show that the mean of Y1, conditional on I equal to 1, X1 equal to X, and Z1 equal to Z, so exactly this mean that we have been looking at before, then becomes equal to another time beta 0 plus X times beta 1 plus, and now we get an additional term, rho times sigma U times this term that we have over here, which is equal to the density of the normal distribution, the standard normal distribution, evaluated in gamma 0 plus X times gamma 1 plus Z times gamma 2 divided by sigma V. And then we divide this whole term over here by the normal distribution. This is density, and this is normal distribution, also evaluated in exactly the same value that we have over here. There are a couple of things to say about this. First of all, we should realize that this thing that we have over here has a special name. It's usually called the inverse Mills ratio. And another thing that we are going to see over here is that at the moment that we're going to look here at the denominator, well, it's not so difficult to see that this thing is actually by itself the propensity score. So if we make this assumption that, well, U1 and V1 are going to be joint normal, then it's not that difficult to see that the probability that V1 is larger than this thing that over here is exactly equal to that thing that we have here in the denominator. So therefore here in the denominator we have the propensity score, and in the numerator we have something which, well, looks like the propensity score, but is now the density instead of the distribution function. Well, you can actually show that this inverse Mills ratio is going to be decreasing with respect to this thing that we have here inside the parentheses. Whereas the propensity score, by the way, is going to be increasing with the thing that we have here within the parenthesis. What does that mean? Well, that means, of course, that this whole term is going to be smaller and smaller and smaller in absolute values at the moment that, well, the propensity score, so the denominator, becomes larger. That's not that difficult to understand, of course, because suppose that this thing that we have over here is very large, which means in the limit equal to 1. Well, then we divide here by 1, but you should take into account that in that particular situation, well, this thing that we have over here, this thing can only be equal to 1 in the case that this thing in between parentheses is large. Must be very large, of course, almost equal to infinity. And that means, of course, that this part that we have over here becomes equal to almost 0. So therefore we're going to see that, well, at the moment that this thing is large, then actually this whole thing that we have over here is small. But suppose that, well, this thing here between parentheses is small, or maybe even negative, well, then you can actually show that this thing is going to be, say, small, so we divide by something small. Even though this thing might be quite small as well, it's actually going to be this, the numerator divided by the denominator is going to be actually quite large. Well, this relationship suggests a two-step procedure, and that was introduced by Jim Hackman in 1979. That's of course an extremely old paper. More recently, but also quite some time ago, in 2000 he actually received the Nobel Prize, well, more or less for writing this paper. And he suggested two-step procedure. What we can do is that we can estimate in the very first step, we can do a probit on the, say, well, on the variable I that we have over here, whether somebody has an observed y or not, on, of course, x and z. And then what we're going to get is essentially nothing else as estimators of the gamma 0, gamma 1 and gamma 2 over here. And we call them gamma 0 hat, gamma 1 hat and gamma 2 hat. So what we're going to do is that we are going to run a regression, a probit regression of whether you, well, in our example, whether you work or not on the characteristics of x and z. And then we get estimators of this thing over here. And then we're going to substitute these estimators into this inverse Mills ratio that we have over here. And then in a second step, what we're going to do is that we're going to run a regression of y on x and on this inverse Mills ratio. Well, then you can show that what you're going to get is consistent estimators of beta 0, beta 1, and actually even of rho multiplied by sigma u. It's even possible to estimate sigma u separately, but generally it is sufficient to actually only know the, say, sign of rho that we have over here. That's the most important thing that we want to know. Since sigma u is always going to be positive, that means of course that at the moment that we're going to see that this, say, the sign of this rho times sigma u is positive, then rho actually is also positive. If it's negative, the coefficient, then rho of course must be negative. Take into account, by the way, that even though we can do this two-step procedure and will give us consistent estimators, we could also have used maximum likelihood instead in this case, because take into account that at the moment I'm going to assume that u1 and v1, they're going to be joint normal. Well, they were the only random variables that we had that we did not observe. That means, of course, nothing else as that we have a fully parameterized model. And we do know that at the moment that we have a fully parameterized model, then the best thing to do, or the most efficient thing to do, is always to use maximum likelihood. So instead of doing this procedure that we have over here, we could also have used maximum likelihood. Still, a lot of people actually use this method that we have over here. That's first of all because of the fact that it's simpler, but that's not the only reason. What we should realize is that one problem with respect to this specification that we have over here is that it only works at the moment that u1 and v1 is joint normal. That's true for this procedure, but it's also true for doing, at the moment that I'm going to do maximum likelihood, then I also use all the information necessary for the distribution, and that means that I use the normality assumption quite intensively. And that means that if u1 and v1 are not going to be normally distributed, why would they be normally distributed? I have no idea. Then we can be for sure that maximum likelihood will become inconsistent. What about this two-step procedure that we have over here? Yeah, most likely also because of the fact that also that is, well, based on this assumption that we have over here. And that, of course, is only true at the moment that we are going to have joint melody. However, one thing that we should realize is that, and that's something that I already said, is that very generally this relationship depends on the propensity score. And since this, say, inverse Mills ratio also depends on the propensity score, whereas we do know that this relationship depends on the propensity score, therefore what we could have done as well is to simply do this two-step procedure. And even though, well, maybe it's not really this relationship that we have over here, we might be already near the relationship that we're going to have, even in the case that there is no normality at all. That is about a paper that is written by Das Nguyen Vella. They actually think about this. They look at what is going to happen at the moment that we do not have joint normality. What can we say about this thing that we have here at the right hand side? And they actually show that as long as you're going to do something with respect to the propensity score, then potentially you will be doing good things. And well, maybe we should not just use here, for example, the inverse males ratio, but we could of course also have used the inverse males ratio squared or something like that. That would actually help us in order to be able to estimate the beta 0 and beta 1 consistently. That's the main reason why people still use the Hackman procedure, with the idea that it might be a good, at least, approximation of a more general semi-parametric model. I would like to go on now to the application. And the application ultimately is going to be from Monaghan and Rubenstein here on this slide that we have over here. But before I'm going to do that, I would like to look at a couple of things which are related to this. And that's, first of all, I have here at the left hand side, I have the different levels of employment for both males and females. And at the right hand side, I have the number of working hours, also here both for males and females. Let's first of all concentrate on the employment levels. At the moment that we're going to look at males, that is here in blue. Then one thing that is immediately clear is that the employment rates for males here in the CPS in the United States, they are quite high. They start here around, I would say, 92 or 93%. And even though they drop a little bit in such a way that we have here even below 90%, it's maybe 89 or 88%, but we should take into account that generally the employment rates of men have been quite high over this whole period of time. We do have some periods in which it declines quite a lot. Here, for example, during the crisis of the 80s. Here also, during the crisis, the more recent crisis, the global financial crisis. But we should take into account that even though there is some variation, and even though we have a slight decline over the period of time, men actually do have relatively high employment rates. The moment that we're going to look at women, well, then we see a completely different picture. First of all, we do see that in 1976, the employment rates for women were at least comparable to, say, men, and also with respect to the period afterwards, it was relatively low. Here we see that the employment rate for women in 1976 was only, well, slightly above 50%. That sounds maybe a little bit low for the today's standards, but you should take into account that this, for the United States, was still relatively high compared to, for example, European countries. I would be surprised if most of the European countries would actually have employment rates that were above 50%. I'm pretty sure that many countries, including the Netherlands, actually had at that time much lower employment rates than 50%. One thing we see as well, looking at this particular picture, is that the employment rates have been increasing quite a lot over time, in such a way that around the year 2000, the employment rate for women was about 75%. After that, it has been decreasing a bit, but more recently, again, it has been increasing somewhat. Well, apart from the employment levels, we can also look at the number of working hours. If we first of all are going to look at men in the United States, then we should conclude that men actually in the United States work quite a lot. We, for example, compare this to men in Europe. Well, already for a couple of decades, men in Europe, they work about 1,700 hours. And here we do see that even for the lowest years, it is still, well, a little bit above 2,000 hours. So that means that men in the United States actually do work quite a lot. Even though there are, of course, we do see that it depends a bit on the, say, business cycle. Here in the in the downturn or the recession of the 1980s, we do see that there was a reduction with respect to number of working hours. This also happened somewhere in the 90s. Of course, also here in the global financial crisis. And this last dip, that is, of course, COVID. The fact that people were not allowed to do their jobs anymore, well, that actually resulted in this thing that we have over here. At the same time, we do see that the number of working hours for women was much lower, starting a little over 1400, but we do see that the, say, working hours have been increasing quite drastically over time. Also here we have the corona dip, but apart from that we do see that there has been a quite strong increase with respect to the number of working hours over time for women. So what you should understand from these two pictures is, especially for the next slide, is that, well, employment figures for men have been much higher than for women, and for women at least they have been substantially below, say, 100%, and that's actually not so much the case for men. Well, then I would like to go on with the application, and that application is from Mulligan and Rubenstein. This is from a paper published in 2008 in the Quarterly Journal of Economics, and what they actually do is that they estimate the Heckman selection model for different years. So for every year that we have with respect to the CPS, they have been estimating the Heckman selection model. Now you might immediately say, like, well, this is very special because of the fact that this paper has been published in 2008 and you actually present now results actually up till 2021. Of course, these are not the, say, original results by Mulligan and Rubenstein. I have changed them a bit, also with respect to specification. But what I have done is that I have run myself, of course, especially the results from, say, 2008 onwards. This is actually published in a recent paper, or actually a forthcoming paper of mine, in the quantitative economics. Well, what we can do is that we can, first of all, now look at the left-hand side. These are actually the estimated rows. So remember that at the moment that we're going to do a Heckman selection model, then in the second stage we are going to run a regression on Y, on X, and on the, say, inverse Mills ratio. And then we're going to get an estimator essentially of rho times sigma u. We simply going to assume that sigma u is equal to 1. Well, then actually what we can do is that we can plot the rows as I have done over here. We're not that much interested anyways in sigma u, so therefore we can simply set it equal to 1, and then we get this row that we have over here. And we see something very special with respect to rho. We see that rho is negative in the, say, 1970s up till the, I would say, the late 80s. Then there's a period of time that we do not exactly know what happens. Could be positive, could be negative. But then from, say, the beginning of the 90s onwards, then it becomes definitely positive. It's already quite high in 2000, and it stays actually more or less so high in the more recent, say, decades. The question, of course, arises, what does this mean? Well, first of all, at the moment that we have a negative rho, that means so-called negative sample selection. What does that mean? Well, that means actually nothing else is that in that particular case, we have a situation in which the women at work actually also have the so-called lowest wages. So that means that the women that work have the lowest wages, the women that do not work have the highest wages. A positive rho means exactly the other way around. Then we are going to be in a situation in which the women that have the, say, highest wages actually work, and those women that do not work have the lowest wages. Well, Mulligan and Rubenstein make a very big point out of this, out of the fact that it is first of all negative and then it turns positive. What I'm going to do is that I'm, in my own words, more or less describe what they say, but take into account that this is not by definition the thing that I think is going to be correct. What I say is that this, say, development that we've over here from negative to positive with respect to rho could be a reflection of the changes with respect to culture, or more in particular, the changes in how people actually perceive women that work. In the 70s and the 80s, it was maybe still the case that, well, working as a woman was not perceived as something positive. And therefore, maybe in the 70s and the 80s, it was the case that the women that worked were essentially the women that, well, actually had to work. They had to work, for example, because of the fact that they did not have a husband, and therefore they had to provide income for themselves or also income for their children at the moment that they were single mothers, and therefore they had the necessity to work. In addition to that, these could also be women that actually do have a partner, that do have a husband, but their husbands might not have so much income. And on the other hand, the women that did not work in the 70s and the 80s were women that actually did not have to work simply because of the fact that they had a husband that had enough income to provide income for not just for the husband themselves, but also for the children and for the wife. Well, if that would be the case, then you might expect something like this thing that we have over here. And that is related to the fact that we have in marriages, not only in the United States, but all over the world, we have something which is related to what we usually say assortative matching. If we're going to look at many marriages, then it's typically the case that, well, the individuals that have the highest potential wages usually tend to marry with each other. And that's also true for the individuals that have the potential lowest wages. They also tend to marry more with each other. And that means, of course, that at the moment that we're going to look at women that have to work because of the fact that their husbands actually are not having enough income, have very low wages, well, that also says something about the wages of these women themselves. They typically also have relatively low wages. So therefore, we might expect that, well, at the moment that we're going to look at the women that work in the 70s and the 80s, well, these were generally women that had relatively low wages because of the fact that they only worked because of the fact that it was necessary. Well, according to Mulligan and Rubenstein, this changed over time in such a way that in the year or around the year 2000, it was more accepted for women to work. And therefore, it was more and more the case that women started to work because of the fact that, well, for them, it was very beneficial for them. And that was especially beneficial for the women that had the highest wages because of the fact that their opportunity cost of not working, staying at home, was actually much higher than for the women that had very low wages. And that is the reason why you actually see over here that many women, well, came into the labor market that had extremely high wages and thereby essentially, crowding out the women that were originally in the labor market, women here at the bottom of the labor market. So therefore we get this relationship that we've over here. I will say much more about this relationship later on and whether I think that this is reliable or not. But we should take into account that this has a big impact on the, say, wage gap, and then especially on how we, well, perceive the changes with respect to that wage gap. Well, we have already looked at the wage gap itself, but so far we have only been looking at the quantiles. So let's now look at the means. Let's look at the mean wage gap. Well, that is drawn here in blue. That is here the raw wage gap, not taking anything into account. So just taking the difference in the mean between the wages of the men minus the wages of the women. Well, then what we're going to get is this wage gap over here. It starts at around, I would say, 53%, and it decreases over time, especially in the 80s and the 90s. Then there is not so much of a decrease anymore, but still what we're going to see there, around the year 2021, the wage gap has reduced to around 21%. So therefore you should take into account that this actually shows that the wage gap, even though of course 31% is still quite substantial, has reduced quite a lot over time. But take into account that this also is, completely based on just taking simple differences in means between men and women. And as we already have seen, well, there might be, we might maybe have to correct for some stuff. One thing we have to correct for is the fact that men and women may be different from each other in terms of education levels, taking into account that, if anything, the education level of women might actually be higher than that of men. But also maybe other things we have to take into account. But another thing that we might have to take into account is selection. Given the fact that we see here, by the way, everything that we have done so far is about the selection of the women, we're not going to look at selection of men for the simple reason that, well, the employment levels of men were actually quite high. So therefore there has not been that much of selection anyways for men. But at the moment that we're going to look at the mean difference in wages between men and women, then we should take into account that what we do is that we are going to compare all the men with only a fraction of the women. For example, here only a little over 50%, but even here we only have around 75% women, whereas almost all the men actually work in that particular year. So therefore, that's not a fair comparison. So what we need to do is that we, for example, could ask ourselves the question, what would actually have been the mean of the women if all the women would have been working like actually the men? Well, that we can actually do in this particular case. And for that, it's best to scroll back to this slide that we have over here. After having, well, corrected for sample selection, that means after having done this two-stage procedure of Hackman, taking running regression on y on x, and on this, say, inverse Mills ratio that we have over here, well, then actually we can predict the wages for everybody, given the fact that these individuals are, well, are working. So what we can do is that for all individuals, working or not, we can predict their wages given their axis that we have over here, because of the fact that then what we can do is that we can simply have beta 0 plus, well, the x multiplied by beta 1. Given the fact that beta 0 and beta 1 are now consistently estimated, they actually give us the, say, wages that we are going to get for everybody after having taken sample selection into account. So for the working individuals, but also for the non-working individuals. That means, of course, that we can take the mean of, say, y, well, just looking at these things that we have over here. Well, that's exactly what we do in this orange curve that we have over here. Now the question, of course, arises, what is then going to happen? Well, that depends on whether rho is positive or negative. If in the case that rho is negative, well, then remember that that means that essentially the lowest paid women, they are going to work. And that means, of course, that at the moment that we're going to bring women into that actually do not work right now, well, these women are going to increase the mean wage because of the fact that the lowest paid women, they work right now. All the women that do not work right now, they have higher wages. So at the moment I'm going to bring these women into the labor market, and I'm going to look at then what then the resulting mean wage is going to be. Well, these women actually had higher wages that came in, and therefore they increased the mean wage of the women. That means, of course, that's going to reduce the mean wage gap because of the fact that the wage gap is the, say, the mean wage of the men minus that of the women. If the mean wage of the women is going to increase after correcting for sample selection, that means, of course, that the wage gap becomes smaller. Well, that is not exactly what you see over here, and that's potentially because of the fact that the rows are actually here negative, but not that negative. We see it a little bit over here that essentially here indeed the, say, corrected wage gap is a little lower than the original wage gap that we have over here. But then it's more interesting to look at this period that we have over here. We see that rho actually increases at a particular moment in time and becomes quite large. And the question, of course, arises, what happens at the moment that rho is positive? Well, then it's exactly the other way around. Then you should realize that at the moment that we're going to look at the mean wage at the moment that all the women work, well, take into account that now at these years, for example in 2010, the best earning women, so the highest earning women are actually working. So at the moment I'm going to ask myself the question, what would be the wage if all the women would be working? Well, that would be lower in that case, because of the fact that women that do not work actually have lower wages. So at the moment that you're going to bring them into the, say, total wages that we have, well, then the mean wage should actually reduce. And that's exactly what we see over here. We do see that at the moment that we're going to look at the wage gap, well, the wage gap should then actually increase, of course, because of the fact that, again, the, well, mean wage gap is equal to the mean wages of the men minus the mean wages of the women. If, of course, the, say, mean wages of the women are going to decrease after correcting for sample selection, then, of course, we're going to see that the wage gap should increase. And that's exactly what we see over here. The moment that we, for example, are going to look at the year 2010, well, then the mean wage gap was, well, around 27% or something like that. But after having corrected for sample selection, we get a much larger mean wage gap. And this results in this picture that we have over here. Here we now see that actually, even though the mean wage gap has been decreasing quite a lot, we see at the same time that the, say, mean wage gap after correcting for sample selection hasn't changed that much. And that's exactly the, say, conclusions that Mulligan and Rubenstein make. Of course, they only have data up till around 2000, 2005, but they concluded that actually the mean wage gap in reality hasn't changed that much over time. So what we do see, of course, is that women have increased their wages quite a lot, but that's only because of the fact that the type of women have changed from the women that had the highest wage, from the women that had the lowest wages to the women that had the highest wages. But that doesn't mean that the women were just better paid. It's just other kind of women that work right now. And we see that, especially in the period that I have been estimating, that it actually doesn't change that much. For example, here the year 2012 and here even 2014, the wage gap wasn't that much different from what we had here in 1976. Well, this is, of course, a very interesting story that the mean wage gap has hardly changed over time, but I think it's also a little bit unbelievable. And the reason behind that is because of the fact that we should realize that at the moment that we're going to look at the observed characteristics, so what is the story behind Mulligan and Rubenstein? Well, the story behind Mulligan and Rubenstein is essentially that here in the 70s, the kind of women that were working were actually very special. They were not rich at all, they were actually poor. They had very bad characteristics, they had essentially the worst talents, and these were actually the women that worked at that moment in time. Whereas the women that did not work, they actually did have very good talents, but the reason why they didn't work was because of the fact that it was not necessary for them to work, because of the fact that they had a husband to take care of them. Well, this could of course be a real story, but that cannot explain the fact that at the moment that we're going to look at the observed characteristics of the women, even in 1976, that the observed characteristics of the working women were actually very good. For example, at the moment that we're going to look in 1976 at the number of women, or the percentage of women that had a college degree, that was around 10%. That doesn't look like a lot, but take into account that even for men, this percentage was not that much higher. It was more or less the same. And the reason behind that is because of the fact that this is a very long period of time ago. It's not the people that were in school, of course, in 1976. These are the people that actually were working in 1976. So they could be in between, say, 25 and say 60 or something like that. So the oldest individuals may actually have had education even before the Second World War. Well, you should take into account that of course implies that we are going to look here at individuals which are, well, now actually very old and had not that high levels of education. Well, among the working women, we see that the 10% of the working women, they had a college degree. The moment that we're going to look at the non-working women, then it was only 5.5%. So the non-working women were not just very talented women that stayed at home, but these were actually women that had lower education levels than what we could say the poor working women, according to Malek and Rubenstein. Well, that doesn't seem to be correct, because of the fact that the, say, working women actually did have much higher levels of education, and to go for higher education, also in these periods of time, you had to have money in the United States to have these kind of high levels of college degree. The moment that we're going to look at an advanced degree, so that's either a master or PhD, then we see that the difference is even larger. Then we see that for working women, this figure is almost 6%, and only 1.7% for the non-working women. So therefore, the story of Malek and Rubenstein seems to me really unbelievable. But the question arises, could we do something instead? Well, one thing that we can do instead is that we could actually use a little bit more information. Many data sets, including the CPS, also have the number of hours worked. So far what we have done is that we only have been looking at, say, the persons who worked and the persons that did not work. Well, at the moment that you have working hours, you could do something else. And Vella, in the International Economic Review in 1993, he shows that at the moment that HI star is larger than 0, then we can look at the mean of Y1, conditional H1 equal to H. Well, we can rewrite the H1 star, but we can also see this as this H, number of working hours itself. And also conditional X1 equal to X and Z1 equal to Z. Well, that's again is equal to beta 0 plus X times beta 1 plus rho sigma U multiplied by this term now that we have over here. So it's almost identical. However, instead of having this inverse Mills ratio, now we get, well, something like this thing that we have over here. Well, this now suggests a completely other method. What we can do now is, instead of doing probit in the first step, instead we can do tobit and estimate gamma 0, gamma 1 and gamma 2, and even this sigma V1 that we have over here. And then what we could do is that we can then, well, substitute gamma 0, gamma 1 and gamma 2 in sigma V. Well, the estimators, of course, so gamma 0 hat, gamma 1 hat and gamma 2 hat, as well as sigma V hat. We can substitute it in this equation over here in order to get now this thing that we have over here. And then in a second stage regression, we can run a regression of y on x and on this thing that we have just estimated. Well, then we are going to get a completely new picture. Then at the moment that we're going to look at the estimated values of rho, then we're going to see now that rho is actually always positive. And it doesn't increase over time. If anything, we're going to see over here that it might decrease a little bit over time, especially since the mid-80s. And this, of course, has a very big impact on the way we should look at the development of the wage gap. Originally, we saw that the wage gap dropped actually quite a lot at the moment that we did not correct for sample selection, but that's no longer the case. Well, we see still that happening at the moment that we do not correct for sample selection, but we should take into account that we have seen that at the moment that we corrected for sample selection, then that was no longer the case. Well, in this particular way, we see a completely different situation. What we see is that because of the fact that rho has always been positive, that means that there has been always positive sample selection, and that means that it's always been the case that the, say, best earning women, these were the women that actually worked. And that means, of course, that at the moment that you're going to correct for sample selection, that the mean wages of the women actually go down. And that means that the mean wage gap should go up. And that's exactly what we see over here. The mean wage gap is always above the, say, raw wage gap in the case that we are not going to correct for sample selection. But the most important thing that we should take into account over here is that, well, the development of the mean wage gap over time is almost identical to the raw wage gap, only that it was always a little bit higher. I would like now to go on with the so-called non-separable sample selection models. And this is much more in line with the quantum regression models that we have looked at so far. And it's also much more in line with my own research. This model now has 4 different equations. The first equation looks a lot like the equation that we already had with respect to the linear regression model. It has a yi at the left hand side, and also this equation is going to be called the outcome equation. And at the right hand side we have beta 0 ui plus xi beta 1 ui. And again we are going to assume that this relationship, or more in particular yi, is only observed at the moment that another random variable I is equal to 1. Then in addition that we have our second equation that here also has an hi star, an unobserved hi star at the left hand side. And on the right hand side we have gamma 0 vi plus xi gamma 1 vi plus zi gamma 2 vi. And then the third equation is going to be additional. It has an hi at the left hand side, and on the right hand side we have the maximum of hi star and 0. Well, the interpretation that we can make with respect to this equation that we have over here is that hi could, in the case that y is going to be the log hourly wages, then hi could be the number of working hours. Well, what we should realize is that even though hi star could be negative, working hours of course can never be negative. And therefore what we're going to do here is that we're going to take the maximum of hi star and 0. That means that this hi that we have over here is going to be censored from below at this point 0 that we have over here. And then finally we have I to be equal to an indicator function. This is exactly the same as what we had before. It indicates that hi star should be larger than 0. What we can see from these 4 equations that we have over here is that there are a couple of differences with respect to the linear regression model. First of all, that's not a very big one. We have here that, well, hi now is an additional equation. But more important is the difference with respect to these 2 equations that we have over here. Now they are random coefficients models rather than the linear regression models that we had before. Well, the idea is exactly the same. And we're going to make the following assumptions. We're going to assume that ui and vi, they're going to be independent from x and z. This again is going to be stronger than what we had in the linear regression model, but you might already have expected that because of the fact that in quantum regression analysis, we cannot just say that u and v are going to be uncorrelated to x and z. Then again, and this is quite in line what we also had with respect to endogeneity, we're going to assume, we're going to define the function h, x, z, and v. And now h, x, z, v is simply nothing else as the right hand side of this equation that we have over here. So it's equal to gamma 0 v plus gamma 1 v times x plus gamma 2 v times z. So we should realize that this actually is nothing else as the right hand side over here for given values of x, z, and v. And again we are going to assume that this function, for whatever this function is going to be, it must be strictly increasing in its third argument. And then finally I'm going to assume that u and v, they're uniformly distributed, as you might already have expected. Well, this assumption that we have over here, the first assumption that we have over here, implies of course that at the moment we would have been able to observe everybody. So if I would have been equal to 1 for everybody, well then we would have been able to just run a regression, a standard quantum regression analysis of yi on this xi that we have over here in order to estimate beta 0u and beta 1u. But the problem again is that we do not have only i's equal to 1. And that means that, if there are at least some i's equal to 0, then the only thing that we can do is that we can, do a quantum regression on the remaining observations. But like what we have seen in the linear regression model, this is not going to work well. And the reason behind that is because of the fact that we should realize that even though we have assumed that u and v are going to be independent from x and z, that is an assumption that we have made on the total population. So for all the, say, observations that we have, not only for those observations for which y is going to be observed. And we can actually show that even though u and v is going to be independent from x and z, u generally is not going to be independent from x and z at the moment that we're going to look at the so-called selected sample, those observations for which h is strictly going to be positive. So you could also say I is going to be equal to 1. This we can quite easily show by looking here at the probability that u is smaller or equal to a little u, conditional on x and z of course, but also conditional on the fact that h is larger than 0. What is this thing that we have over here? Well, the first thing we can do is that we can substitute in, well, we do know that if h is larger than 0, then h star must be larger than 0, so that means that this whole thing that we have over here must be larger than 0, so then we get this thing over here. Now we should realize that this x of course is equal to that x that we have over there, then one is equal to little x, so also this thing is equal to little x. And the same we can say for set. This set over here is equal to that set that we have over there, that one is equal to little z, so also this thing is going to be equal to little z. Now what we can do is that we can write this thing that we have over here based on the definition that we had at the previous slide. We can write this as h, well, evaluated in x, z, and this large v that we have over here. So take into account here that x and z are given, they're given values to us, and therefore this, say, h is essentially only a random function in this random variable v that we have over here. Now we can use the fact that we have assumed that h is strictly increasing in its last argument in this v that we have over here, which means that we can take from the left and the right hand side, we can take inverses. So then we get here simply v, and on the right hand side we get the inverse function of h with respect to x, z, and this 0 that we have over here. So we can also write it now like this. And then we can use the fact that we do know that u and v, they're independent from x and z. So therefore we don't have to here condition on x and z as we do over here. We can even write it like this. And even though this looks a lot simpler than what we had seen before, the thing that we have over here, you should realize that this actually does depend on the outcomes of x and z. And that means, of course, that the distribution of u depends on, say, the outcomes of x and z, so therefore they depend on x, z, as we have written down over here. Unless, of course, u and v are going to be independent from each other, but that's, of course, a very restrictive assumption to make that we don't actually want to make in this particular model that we have over here. This has important consequences. Among other things, this is going to have a very big consequence on the, say, possibility to estimate or to do empirical investigation in general. For example, one of the things that we could do is that we might be interested in this thing that we have over here, the probability that beta 0u plus beta 1ux is smaller or equal to y, conditional on h larger than 0. What is this thing that we have over here? Well, we should realize that this actually has a very nice interpretation. This actually, given the fact that we do of course know that y generally is equal to beta 0u plus beta 1ux, here we have fixed x, which essentially means that we're going to look at a counterfactual distribution of how the, for example, wages would have looked like in the case that everybody has in our, say, population has an x equal to this little x that we have over here. So one thing that we could have done for empirical research is that we can ask ourselves the question, how would a distribution of, say, our population have looked like if everybody is going to have, say, a college degree? And the reason behind that is because of the fact that we could actually compare that to a situation in which nobody has a college degree. So this, well, probability that we have over here generally is a very interesting thing, and is of course related to the idea of quantiles. This is essentially the conditional distribution, or it's the distribution of, in the case that we have this x over here, but we could of course also look at the quantiles of this thing over here. But take into account that this thing here at the left hand side is different from what we have here at the right hand side, and that's a subtle difference. You should take into account that this is going to be the distribution of what we expect at the moment that everybody has an x equal to little x, whereas this distribution that we have here at the right hand side, given the fact that we condition here an x equal to little x, this is actually the distribution among the individuals of y, of course, among those individuals that have an x equal to x. So this, for example, is the, say, wage distribution among the individuals that have a college degree. And that's, of course, quite different. The distribution that we expect at the moment that everybody has a college degree in our analysis or in our sample is, of course, different from the distribution of wages among those individuals that do have a college degree. And what we should realize that this thing over here actually has, well, this thing that we have over here, well, is related to empirics, whereas this one that we have over here is not equal to that thing that's over there. In order to understand that, one thing we can do is that we can realize that we can also write this x that we have over here, we can simply write it as a large x, and the reason behind that is because of the fact that we can always go back to what we had. So if I write it now as with a large x, well, then we should realize that this thing that we have over here, I could of course have gone backwards because of the fact that here this large x can of course be written another time with a small x because of the fact that I have this conditioning over here. But take into account that this thing that we have over here is actually nothing else as y itself. We do know that the definition of y is equal to beta 0u plus beta 1u times this stochastic x that we have over here. So we can even write it like now this. But this, what we have here at the right hand side, is, as already said, it's the distribution of wages among those individuals that have an x equal to little x. And of course an h larger than 0, otherwise we would not have observed this y in the first place. We should take into account that this thing that we have over here has empirical content. This is something that we can observe, of course, but it's not maybe the most interesting thing to look at. It's more interesting to look, for example, at what would have happened in the case that everybody would have had, say, a college degree. But we should take into account that these two things are not equal to each other. That brings me to estimation. It's immediately clear that, well, estimating this model is not going to be that easy. However, in a recent Journal of Econometrics article, actually an article that is still forthcoming, I prove with the two co-authors that we can actually write V as being exactly identical to the distribution of H, say the number of working hours, conditional X and Z, and then also evaluating H, X and Z. This is going to be very valuable. And the reason behind that is because of the fact that V is of course unobserved. V is unobserved, but we should take into account that even though the left-hand side over here is also unobserved, and the reason behind that is because of the fact that we do not know this distribution function over here, we can in fact try to estimate it. And that's exactly the same idea as what we had when we were looking at the daily. Remember there also that we were interested in V, and we could actually there also write it as a distribution function. But now it's a distribution function of H, H, conditional X and Z, but also evaluating these three values that we have over here. Well, based on this, we actually show also in our Journal of Econometrics article that then U is going to be independent from X and Z, conditional H larger than 0. Remember that, well, generally U is not independent from X and Z, conditional H larger than 0, but we make it independent again by, well, having this additional conditioning on the values of V that we have over there. And we should realize that this of course makes the V going to be a good control function. Well, we should realize that V of course again is unobserved, But as I already said, we can try to estimate this thing that we have here at the left hand side. And that gives us the following estimation procedure. First of all, we're going to do a regression of, a distribution regression of h on x and z. And then we are going to be based on this relationship that we have over here, we're going to predict the v hats, which are actually nothing else as the estimated, well, distribution functions that we are going to do with respect to this distribution regression over here, evaluated in the observed h, x, and z. And then in a second straight regression, we're going to run a regression of y on x and on v hat. Well, that gives us the opportunity to look at counterfactual distributions. This actually comes from another forthcoming paper by me. This is from a paper that I'm going to publish in quantitative economics. And based on these counterfactual distribution, I'm not going to show how we are actually going to do that, because of the fact that that still has a lot of mathematics, and also due to time, I'm not going to explain that over here. But based on that, we can decompose the differences in the distributions in, well, a selection effect, a structural effect, and a composition effect. Remember that when we were looking at standard distribution regressions, I said that the distribution in distributions, the difference in distributions can be summarized by a so-called structural effect and a composition effect. And the structural effect, I already said, is the differences that are due to differences in the conditional distributions, essentially the differences in terms of payments, in terms of the wage structure, and the composition effect is due to the difference in the characteristics, in the composition of the workforce. However, in addition to the structure and the composition effect, in this selection model, we can also look at the so-called selection effect. The question arises, what is the selection effect? Well, you should realize that due to the fact that more and more women entered the labor market in the United States over time, well, that had an impact with respect to their, say, wage distribution. At the moment that we are going to assume, and that's the most realistic thing to assume, is that the selection is going to be positive. That means, of course, that the most, say, productive, the highest earning women actually work. And we should then realize that, well, that means, of course, that since in 1976 not that many women were working, well, these were, say, the women that had the highest wages at that moment in time. Over time, more and more women entered the labor market, but they actually did have lower wages than the women that were already working, and that must have lowered the, say, wages, must have shifted the wage distribution to the left. And that means that we can expect that the selection effect is going to be negative over time. I would like to go on with the application, and that is again an application with respect to the CPS. And these are actually results to be published by me in quantitative economics. What we do here is that we look actually only at the wages of the women, which is actually not reported in this particular slide. And what we're going to do is that we're going to look at the mean and the median. And we do see that at the moment that we're going to look at the total, well, impact on the wages, the real wages, then we do see that there has been quite a large increase with respect to these real wages for the women at the mean, but also at the median. And at the moment that we would like to explain this, then we see that this can be mainly explained by the so-called composition effect, the fact that these women became more educated over time, that resulted in a increase of these wages. We do see that there is also a structural effect, but the structural effect is mainly, at least in the beginning of this period of time, it's quite negative. Then at a particular moment in time, it does turn positive here around the turn of the century. It turns negative again at the moment that we're going to look at the global financial crisis, and then it increases in the last couple of years, but take into account that I do not have the year 2021 and the year 2022. Well, At the moment we're going to look at the mean compared to the median, then we don't see that much of differences over here. Then finally the selection effect. Also these are almost identical for the median and mean, although they're a little bit more negative for the median than for the mean. But the negativity, the fact that these selection effects are negative, that's something that we could have expected. And the reason behind that is because of the fact that I said that more and more women actually enter the labor market here over time. That's something that we have already seen before. And what we can expect is that there was so-called positive selection for these women. That meant that essentially the women that were already working in 1976 were in fact the women that had the highest wages. And the women that entered the labor market, they still maybe had high wages, but they were at least lower than the women that were already at the labor market. And that means, of course, that these selection, the fact that more and more women entered the labor market, that resulted in a so-called negative selection effect that lowered, in fact, the wages of the women. We see that at the mean, and we also see that at the median. At the moment that we're going to look now at the bottom of the wage distribution, then we can look at D1, the first decile, as well as Q1, which is the first quartile. We do see that most of the impacts are just a little bit more dramatic. First of all, we do see that the increase in the real wages has not been so large at D1 and Q1 as they were at the median and the mean. And we do see that the composition effect can completely explain this, or actually even over-explains it, because the composition effect generally is much higher than the total effect. We see that at a D1 and we also see it at Q1. That means that the structural effect generally is negative over here. It only turns positive here at the very last year. Again, that's true for D1 and actually also true for Q1. In addition to that, we do see that the selection effect now is somewhat more negative from what we have seen at the previous slide. That is again true for D1 as well as for Q1. Well, this is also something that we might have expected. As I just said, the women that entered the labor market over time actually were women that had relatively low wages, or at least they had lower wages than the women that were already working. And that means that they actually entered the labor market at the bottom of the wage distribution. And that means, of course, that we can expect that the wage distribution at the bottom is going to be more affected. So the wage distribution at D1 and Q1 is going to be more affected than the part of the distribution that is a little bit higher up in the distribution. Then finally we can look at the upper tail of the distribution. Then we can look at Q3 and D9. Well, first of all, focusing on Q3, we do see that Q3 has increased quite a lot, and it again can be almost completely explained by the composition effect. We do see that the structure effect sometimes is a little bit low and even turns negative, but generally it is positive. And finally, selection effect. Well, the selection effect is actually not that important anymore, which we might have expected because of the fact that here we are really at the upper level of the, say, wage distribution. The moment that we are going to look at D9, then we do see that again there is quite a large increase with respect to the wages, the real wages over time. And even though a large part of this can be explained by the composition effect, now also the structural effect becomes important, and again the selection effect is more or less equal to 0. Then we can also look at changes in inequality. We can look at the interquartile range here at the left and the interdecile ratio at the right. So it means actually nothing else that we are going to look at the Q3 over Q1 for the interdecile ratio. For the interquartile ratio, of course. And for the interdecile ratio, we're going to look at the difference between, or D9 divided by D1. We see that, interdecile ratio has increased a little bit faster, and we also see that, especially at the beginning of our sample period, the structure effect explained that quite a lot, and that is actually what we might expect because of the fact that we have already seen that the, say, structure effect in this period for these say individuals, for these individuals that live over here in D9, did not have such a big impact, but it did have a really large impact here at D1. So I'm sorry, D1 that we have over here, of course. So that means that we can expect that, well, as we have over here, that the structure effect can have, well, explain a lot of the change in the inter-decile ratio. We see that it's still important over time, but another thing also becomes important over time, and that's the composition effect. Then finally, we do see that the selection effect is positive, and that is something that we also could have expected because of the fact we do know, looking at the previous pictures, that at the bottom of the weight distribution there was a negative selection effect, whereas at the top of the weight distribution this effect was more or less equal to 0.